The Internet operates as a rigid, highly regulated transport network. It relies on a precise physical and logical architecture to move massive volumes of data across the globe in milliseconds. But if you freeze that highway and zoom into a single transmission, the abstraction falls away. The macro network dissolves into microscopic, raw data, a single packet in transit. To secure a system, you have to adopt the perspective of the master architect. You need to know how gateway routers and IP addresses direct every byte along a defined route through this massive structural intersection. But you also need the perspective of the infrastructure engineer. You have to understand that true vulnerabilities live inside the microscopic details, the specific header flags, the bit fields, and the raw hexadecimal mathematics that make up the packet itself. To map, defend, and ethically hack network infrastructure, an analyst must master the TCP/IP stack in its entirety, operating simultaneously at the scale of a global IP highway and the precision of a single 1-bit flag. This diagram outlines the 4 distinct layers of the TCP/IP protocol stack: application, transport, internet, and network. While the older OSI model uses 7 layers, TCP/IP consolidates them into these 4 functional tiers. When a program transmits information, the data moves down the stack. Through a process called encapsulation, each layer adds its own specific routing and formatting instructions before passing it down to the physical network pathway. Looking at this structure from the architect's perspective, the transport layer operates as the critical logistics hub. This is where data is chopped into individual segments and assigned a delivery method. The primary method for high-speed delivery is the User Datagram Protocol, or UDP. UDP prioritizes pure speed over confirmation. It sends data without verifying if the receiving node is actually listening, operating as a connectionless fire-and-forget protocol. From the engineer's perspective, securing data requires a different approach, the Transmission Control Protocol, or TCP. TCP is connection-oriented, requiring a formal, verified introduction before it will transfer a single byte of payload. This introduction relies on a strict 3-way handshake. In Step 1, Host A sends a packet with the Synchronize, or SYN flag set, querying if Host B is active and listening. In Step 2, Host B receives the packet and replies with its own SYN packet, while also setting an acknowledgement flag. This creates a combined SYN-ACK packet, confirming it is ready to receive data. In Step 3, Host A receives the SYN-ACK and sends one final ACK packet back to Host B. The connection loop is complete and secure data transfer begins. During the first 2 steps of this handshake, both computers generate a 32-bit initial sequence number, or ISN. This tracker allows the receiving node to correctly reassemble large payloads that were broken apart in transit. While this handshake enforces reliability, it creates a predictable mechanism. If a threat actor can calculate or guess the initial sequence numbers exchanged between 2 active nodes, they can step directly into the verified connection, executing a network session hijacking attack. Here, we have a schematic diagram of a standard TCP segment header. This microscopic architecture is exactly what encapsulates the data as it moves through the transport layer. Look closely at this specific block of 1-bit control flags. Each flag occupies exactly 1 bit of the segment, set to either a 0 for off or a 1 for on. The S represents the SYN flag, initiating the session. A is the ACK flag, acknowledging received data. P is the push flag, built to deliver data directly to the application layer. U is the urgent flag, marking data that requires immediate processing. R is the reset flag, used to immediately drop a connection. And F is the finish flag, signifying the transaction is complete. These single-bit fields dictate the behavior of the connection. Threat actors systematically scan these flags, manipulating the 1s and 0s to provoke error responses, allowing them to map out an organization's internal vulnerabilities based on how the server reacts. Zooming back out to the architect's perspective on the top row, we see the 16-bit fields for the source and destination ports. A port is a logical loading dock assigned to a specific process requiring network connectivity. The TCP/IP protocol allows for up to 65,535 possible ports. Security analysts memorize the specific, well-known ports that see the heaviest traffic and the most attacks. File transfer protocol on ports 20 and 21. Secure shell on 22. SMTP email routing on 25. DNS resolution on 53, and web traffic on HTTP port 80 and HTTPS port 443. Internal networks operating on Microsoft architecture require strict monitoring of legacy services. Remote procedure calls operate over port 135, and the NetBIOS session service shares resources across port 139. An open port, combined with a predictable TCP flag response, provides a literal invitation for unauthorized entry. Understanding this microarchitecture is step 1 in any rigorous threat modeling exercise. Moving down to the internet layer, we encounter the macro routing environment. Gateway routers manage traffic between entirely distinct network clusters, relying on logical IP addressing to find the correct physical destination. A standard IPv4 address consists of 4 bytes, or octets. These 32 bits divide the address into 2 distinct components: the identity of the wider network and the identity of the specific host computer. Depending on how many bytes are assigned to the network, addresses are divided into specific classes. Class A reserves 3 bytes for the hosts, supporting massive government or enterprise networks. Class B splits the address evenly for large corporations. Class C dedicates the first 3 bytes to the network, leaving exactly 254 available host addresses for small businesses. To maximize efficiency and isolate sensitive systems, network engineers rely on subnetting. This allows an administrator to carve large network blocks into smaller, strictly partitioned segments. This partitioning requires a subnet mask. When viewed in binary, the subnet mask overlays the IP address, using a solid block of 1s to identify the network portion and leaving the 0s to dictate the available hosts. Because standard class allocations waste millions of unused addresses, the industry adopted classless interdomain routing, or CIDR notation. CIDR bypasses rigid class structures, allowing administrators to define custom subnet boundaries on the fly. A CIDR prefix explicitly states how many bits belong to the network. A /24 prefix assigns exactly 24 bits to the network. This perfectly matches a Class C equivalent, providing exactly 254 usable hosts for that specific subnet. Even with efficient CIDR allocation, the world exhausted its supply of IPv4 addresses. The solution is IPv6, expanding the address space to 128 bits and providing billions of unique addresses for modern hardware. But this massive upgrade in routing architecture creates a severe blind spot. Many older firewalls and intrusion detection systems were built exclusively for IPv4. Because they cannot properly parse the 128-bit structure, malicious IPv6 traffic routinely bypasses legacy filters completely. When an active breach occurs, logical diagrams offer no help. An analyst has to be able to read and manipulate the raw mathematical data embedded in the actual packet payload. All computing logic reduces down to the base 2 binary numbering system. Every value is represented by a sequence of distinct 0s and 1s. Because reading raw binary strings is visually dense and prone to human error, analysts condense it into the base 8 octal system. By operating with digits 0 through 7, Octal cleanly groups binary data into manageable 3-bit chunks. This 3-bit structure dictates Unix file permissions. When an administrator types chmod 777, they are applying the octal value 7 to 3 different user groups. In binary, 7 is 111, which flips the bits to grant read, write, and execute permissions across the board. For deeper network analysis, security professionals rely on the base 16 hexadecimal system. Hexadecimal condenses an entire 8-bit byte into 2 highly readable characters, splitting the byte into what is known as a nibble. It counts from 0 to 9 and then uses the letters A through F to represent values 10 through 15. This compact format is the standard language of bare metal packet capture analysis. Analysts reading a hexadecimal dump can parse the data to identify malicious payloads hidden inside standard network traffic. Finally, the base 64 numbering system encodes binary files into standard text characters. This is the primary method for securely transporting attachments through email protocols. Threat actors exploit this exact encoding specifically to obfuscate their attacks. By translating a malicious binary script into a base 64 string, they disguise the payload as harmless text, slipping it right past automated perimeter defenses. Defending a network requires complete fluency in both extremes. A security professional must understand how to map and route traffic across macro IP highways while simultaneously interrogating the microscopic hexadecimal cargo and single-bit flags of every packet.